Alright, this is our last video for integration by parts. Hopefully you all are making sense of all this. I know it's real tricky being stuck at home with all the ice and the snow, but we're just going to make the best of it. Two more examples here. So this first one, I've got integral of x squared times natural log of x dx. And as always, first thing you want to do is figure out what you want u and dv to equal. And based on what you choose, what are du and v. Okay, so you got a lot of options. You could let u equal x squared. The derivative of that is pretty simple. However, when you let dv, if you did let u equal x squared, then I'm going to put that in pencil here. So here's a guess. Let's say we guess u equals x squared. Then dv would have to be ln of x dx. Now we haven't really worked a whole lot with the integral of natural log of x. In fact, I think in order to prove that one, you actually have to use integration by parts in a real clever substitution. Point being, this is kind of annoying to take the integral of to find what v is. So let's reevaluate. Maybe let's let u equal natural log of x and dv be x squared. Now, you might be thinking, wait a second, every example you've worked so far, you always let u equal some power of x, and then it got simpler. Yeah, that's true. But that's not like how you always have to do it. Every problem is a little bit different. Now, let's see what happens when we take the derivative. Okay, u prime over u, that's 1 over x dx. And then the integral of this thing is going to be, I should have a dx on there, x cubed over 3. Okay, yeah, I know, got a little more complicated, but this thing is dividing by a power of x, and I know I'm going to have a v du somewhere because integration by parts is uv minus integral of v du. When I multiply those together, that's going to make life a lot easier because I'm going to have a pretty simple polynomial to work with. So plugging it in to our pattern for integration by parts, that's going to be u times v, I'll put that up front, minus the integral of v du. Alright, that's actually going to work pretty nicely from here on out because those x's will reduce there, so that's minus a third of the integral of x squared. Oh man, that's not so bad to deal with. So x squared, or cubed rather, natural log of x over 3, and when you integrate that, you'll get x cubed over 3. Should make a ninth there. And then don't forget your plus c. And as always, if you're not sure if you're right, you should be able to find y prime pretty quickly. In fact, I highly suggest it. We're going to be coming pretty close to that AP exam in like, what, 2.5 months or something? So not a bad idea to practice those derivative rules in addition to all these integration techniques. Okay, one thing I just want to add to this one is whenever you're finding definite integrals, like if this said evaluate from, I don't know, let's say 3 to 10. Okay, what you don't want to do is using a change of variables each time and having to redefine those limits of integration. What I would do instead is ignore the limits for the time being, evaluate the indefinite integral, and then you can just ignore that plus c. You can just evaluate it from 3 to 10. For example, let's say they gave you that exact problem. You can leave that there. So let's say that they gave you the integral from 3 to 10, x squared natural log of x dx. Okay, what I would suggest is say, you know what? I'm going to work out just the indefinite integral and do all my work, blah, 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 just like we just did, and then see, oh, my answer is going to be x cubed ln of x over 3 minus a ninth x cubed plus c. Okay, so what that means for us is we can go back to this and say, alright, that's going to equal that antiderivative evaluated from when x equals 3 to x equals 10. So basically what I'm getting at is the definite ones, when you have to do them by hand, which you very well might have to, just work out the indefinite one and then plug your answer, quote unquote, into this original problem and then just evaluate from 3 to 10. It just saves you a lot of time. It's a lot less annoying to take that approach. Okay, last example for integration by parts. This one is going to make your head spin a little bit because we are going to go kind of in a circle. So let's see, we want to figure out what we want u to equal and dv, and then we'll see what happens to du and v. Okay, so we got a lot of options here. If we let u equal e to the x, du is going to be pretty simple. That would mean that dv would have to be cosine of 2x dx, which we can find the antiderivative of. We just have to worry about, that's not just cosine of x, there's a 2 in that argument. So we're going to have to worry about some constants to multiply and divide just to balance things out. Possible, but it seems like it's going to get a little complicated, so alright, instead I'm going to let u equal cosine of 2x and dv be e to the x. Okay, let's see what happens here. Now when we find the integral or antiderivative of e to the x dx, that's just e to the x. And when I take the derivative of that, that's going to be minus 2 sine 2x. Hopefully you're not wondering where that negative 2 came from. The minus comes from the rule for cosine and its derivative. The 2 comes from chain rule. So just remember cosine of u, the derivative would be minus sine of u times du dx. So you've got to take the derivative of that argument and then multiply that in. Okay, so let's see what that gives us. That's going to be u times v, or v times u, doesn't matter, minus the integral of v du. Okay, so that's going to be plus 2 e to the x sine of 2x dx. I just factored the negative 2 out and then changed the order. You don't have to do that, just makes things a little simple. Okay, so it looks like we got to keep going because we still have a product of functions inside my integral. So I'm going to take the same approach, u dv du v. I'm just going to keep going the same way I did. So I let dv be e to the x dx, antiderivative is e to the x. Now I have sine of 2x, and the derivative is going to be positive 2 cosine of 2x. I've seen cosine of 2x somewhere. Okay, now just going to underline this and then bring it down here. So that's going to be all of that stuff from the beginning, plus 2 times, okay, u times v minus the integral of v du. So there's 2 e to the x. Okay, so hopefully at this point you might say, wait a second, we went in a circle, because we did. This is the exact same integral that we started with. Yikes. Okay, so how are we going to proceed? Well, the answer is a lot simpler than you might think. First, let's distribute this 2 in, and then we're basically just going to solve an equation. So I'm going to write out what we have. This integral equals all of this which equals all of this. So the transitive property from geometry says the integral e to the x cosine of 2x dx equals this thing plus 2 times this minus 4 times this integral. All I did was distributed that 2 in, and I set my equation up. Again, you're probably puzzled, thinking, but wait, this equation doesn't make sense. I've got the same thing on both sides. You do, but with different coefficients. So the trick here is I'm going to add this integral on both sides. And those cancel. So now I have 5 of that integral. And the original question said, find this integral, evaluate it. Okay, I'll just divide everything by 5. So that means that integral they asked me to find is 1/5 of all of this. Plus whatever constant I can imagine. And if you're not quite convinced, take the derivative. You better get this thing when you're done. So problems like these are really interesting. And again, when math teachers say interesting, that means hard, difficult, scary, whatever adjective you can associate there. But typically, you're going to come across problems like this. Whenever you have some e to the whatever, and you have a trig function, a periodic function, where it's going to bounce back and forth between sine, cosine, or secant, cosecant, whatever the case might be. And most often, what you're going to have to do is set up an equation like this one and solve for that integral, just like you would solve an equation from like Algebra 1. The only difference is solving for an integral. Alright, hopefully all of this helped. I hope everyone's doing well, and I will see you all next time.